Imagine you're the lead infrastructure engineer at a startup. It's a Tuesday morning. Your app just went completely viral, and you've suddenly hit like a million concurrent users.
Oh, that is the dream, right? But
Yeah.
also the absolute nightmare.
Right, exactly, because your monolithic single node database is just screaming. I mean,
Yeah.
CPU utilization is at 99%. Queries that used to take 3 milliseconds are now taking like 4 seconds.
Yeah, and your AWS bill is just spiraling out of control while this is happening.
Oh, totally. And your CEO is, standing over your shoulder asking if they need to call a press conference to apologize for the downtime. And the choices you make in the next 5 minutes, whether to try and shard that massive relational table or migrate to a NoSQL document store on the fly or denormalize your analytics data, it will literally either save the company or kill it.
It really will. And the brutal reality of that exact moment is that there is no time to consult a textbook. You either have a rock-solid mental model of distributed systems physics or you don't.
Right.
Because when the database melts down, you're fighting the physical limits of hardware. You're fighting the speed of light in fiber optic cables and, well, the fundamental mathematics of network topology.
And that terrifying scenario is exactly why we're doing this deep dive today, because we've got our hands on this really comprehensive 38-slide internal blueprint, and it's designed to prepare engineers for the Google Cloud Professional Database Engineer certification.
Yeah, PDE, it's a beast.
It is, but we aren't just treating this like a study guide, right? We're treating it as almost like a reverse engineered map of how one of the largest tech companies in human history organizes the cloud universe.
Right, because it shows how they train their elite engineers to make those life or death architectural decisions. Taking a magnifying glass to this material, it really reveals the underlying philosophy of modern cloud architecture.
And diving into certification materials is often like drinking from a fire hose, but it's honestly the ultimate cheat code.
It really is. It forces us to ask the structural questions, Like, why do we have 20 completely different ways to store a single piece of user data?
Right.
What are the actual physical trade-offs when we move from, like, a traditional server rack in a basement to a globally distributed serverless infrastructure? So by dissecting this today, you're going to build a framework for understanding why data behaves the way it does at a planetary scale.
Exactly. So whether you're actively prepping for the exam or looking to transition into cloud architecture, or you just want to understand the back end of every single app you use every day, this deep dive is going to equip you with the why behind the what.
Absolutely.
So diving into the blueprint, it starts by establishing a very aggressive boundary. I mean, it draws a massive, uncrossable line in the sand between two roles that, to an outsider, sound completely identical.
Right. The database engineer and the data engineer.
Yeah. The text explicitly states that a database engineer focuses entirely on storage services, migrations to Google Cloud Platform, high availability, performance, and durability. And it puts this in bold letters: no machine learning skills required.
None at all. Yeah. Which is so interesting because the separation of those two roles represents a major maturity milestone in the tech industry.
How so?
Well, for a long time, the prevailing wisdom was just if a person touches data, they do everything from building the hard drives to writing the predictive algorithms. But at enterprise scale, that is physically and cognitively impossible.
Okay, but let's unpack this for a second, because if I'm a startup founder, I'm probably doing both, right? Isn't this just like a corporate separation for massive companies?
At a small scale, sure, you wear every hat.
Yeah.
But at enterprise scale, the database engineer is the architect of the operational vault. Their entire world is governed by latency, input-output operations per second, disaster recovery.
Yeah.
They're ensuring that when a customer swipes a credit card, the transaction is recorded in less than 10 milliseconds. And that record survives a massive power grid failure.
So they are building and defending the actual transactional engine.
Exactly.
Yeah.
Meanwhile, the data engineer is entirely focused on the aftermath. They take the data after it's been safely stored, and they build ETL pipelines.
Extract, transform, load.
Right. They're writing complex Python or JavaScripts to move terabytes of raw transactional records into data warehouses, cleaning it, preparing it so that the machine learning models can actually ingest it without, hallucinating.
I love that. The easiest way I can conceptualize this divide is it's like the difference between keeping the patient alive versus analyzing the patient's long-term health trends.
Oh, that's a perfect analogy.
Yeah.
The database engineer is the trauma surgeon in the ER. They just need the database heartbeat to be steady. They don't care about the patient's diet history over the last 10 years, right?
Oh, they care that the blood pressure is stable right this second.
Exactly. And the data engineer is the epidemiologist looking at 10 years of records across 1 million patients to predict the next outbreak. Operating a high-throughput, zero-downtime database requires an obsession with hardware limits.
Right, and building a data pipeline requires an obsession with statistics and software engineering. Google separates them because you physically cannot hold both contexts in your head when a system is processing 1 million requests a second.
You'd go crazy trying.
Yeah. So let's look at how Google actually tests these trauma surgeons. The exam mechanics outlined in the deck are pretty intense. It's a 2-hour gauntlet, 50 to 60 multiple choice questions. They estimate you need 80 to 150 hours of dedicated prep.
And the resulting certificate is only valid for 2 years.
2 years? That feels so short.
It is short, but it's a stark reminder of the deprecation cycle in cloud computing. I mean, a perfectly architected solution in 2024 might be considered an inefficient, super expensive legacy anti-pattern by 2026.
Just because a new serverless abstraction was released?
Right. But the format of the questions is where the real engineering challenge is. These aren't vocabulary tests. They are highly complex, multivariable scenario questions where 2, 3, or sometimes all 4 of the answers are technically feasible ways to solve the problem.
Okay, wait. If I'm looking at a question and 4 different database configurations will all technically store the user data, how do you even begin to find the correct answer?
Well, there's no penalty for guessing, but you really have to optimize for the hidden constraints in the prompt. Technical feasibility is just the bare minimum. The exam and the real world honestly asks you to optimize for cost, or for operational overhead, or for recovery time objectives.
So you're acting as like a forensic accountant for compute resources.
Exactly. The material heavily advocates for a process of elimination based on identifying the most restrictive business requirement first.
Let's put that to the test. Let's use that specific public parks exam question from the material.
Oh yeah, that's a great example.
So the prompt describes an application that needs a read-only global database of public parks. It's updated nightly by a centralized batch job. And the absolute hard constraint given is that you must select an open source SQL-compliant database.
Okay, so SQL and open source, got it.
Right. And the choices they give are Bigtable with multi-region clusters, memory store for Redis with multi-zones, Cloud SQL for Postgres with cross-region replicas, or Cloud Spanner with a multi-region configuration.
So the fastest way to filter this is to look at those data structure requirements. The prompt demands a SQL-compliant open source database. If we look at option A, Bigtable, we hit an immediate wall.
Because it's a NoSQL.
Right. Bigtable is a wide-column NoSQL store. It's designed for massive analytical or time series workloads, like ingesting millions of IoT sensor readings a second. It doesn't use standard SQL, no relational tables, and it's a proprietary Google product.
Okay, so Bigtable is immediately out. What about option B, memory store for Redis? I immediately flag this because Redis is an in-memory data structure store, right?
Exactly. It's essentially a hyper-fast caching layer. You use it to store ephemeral session data so you don't hammer your primary database.
Trying to use an in-memory cache as your permanent global system of record for park data just seems reckless. Plus, it doesn't offer robust SQL querying capabilities.
Yeah, the physical volatility of RAM makes it totally inappropriate for a primary system of record without extreme configuration.
Ugh.
So it fails the SQL constraint anyway. That leaves us with the 2 heavyweights, Cloud SQL for Postgres and Cloud Spanner.
And both of those are robust relational databases.
Yes, both handle standard SQL queries. Both can be configured to serve read requests globally, which satisfies the requirement for the worldwide application.
But, and here's the catch, Spanner is Google's crown jewel. It's this proprietary, globally distributed relational database. It is a marvel of engineering, but it is fundamentally closed source.
Right. You cannot run Spanner on your own laptop or migrate it directly to AWS without a massive re-architecture.
But Postgres, conversely, is the quintessential open source relational engine. So since Cloud SQL is just Google's managed wrapper around the open source Postgres engine, option C is literally the only logical survivor.
And the secondary clues in the prompt validated Postgres too. It mentioned the database is read-only globally, but updated by a centralized batch job nightly. That is a massive hint about eventual consistency.
Oh, because if the data only changes once a day, you don't need the ultra-expensive synchronous global write capabilities of Spanner.
Exactly. You can have a single Postgres primary database that processes the nightly batch update and then asynchronously pushes those updates to read replicas around the world over the next few minutes.
It's because the latency of an asynchronous update doesn't matter for Park data that only changes every 24 hours.
Right. Breaking down the scenario like that really shows why a massive, like 30% of this entire exam is dedicated purely to Cloud SQL.
It's the absolute workhorse of the cloud. I mean, when a legacy enterprise finally decides to shut down their physical data center, they're usually running thousands of instances of MySQL, Postgres, or SQL Server.
Yeah, they are not going to rewrite millions of lines of application code to use a NoSQL document store. They just want to lift and shift their relational tables into a managed service.
And the database engineer's life revolves around managing that transition. They have to understand how to handle connection pooling when, thousands of microservices try to talk to a single Postgres instance simultaneously.
They have to manage identity and access management policies, IAM, to ensure the web tier can read the data, but only the admin tier can write to it.
And orchestrate automated failovers so that if the primary zone in Virginia goes completely offline, a standby instance in South Carolina promotes itself without dropping a single user transaction.
There's a lot of pressure. Now, the blueprint also heavily emphasizes Cloud Spanner, which makes sense given its complexity. But what stood out to me was the glaring minimization of BigQuery.
Yes, I noticed that too. BigQuery is arguably the product that put Google Cloud on the map for most developers. It's this serverless data warehouse that can query petabytes of data in a few seconds. Yet the certification material actively downplays it.
Well, this brings us right back to the trauma surgeon versus the epidemiologist. BigQuery is the ultimate epidemiologist's tool. It's an online analytical processing engine, or OLAP.
So the transactional database engineer might configure the changed data capture stream that pipes the raw data into BigQuery.
Right, but the moment the data lands in that warehouse, it becomes the jurisdiction of the data engineer, writing those massive multi-page SQL queries that aggregate 5 years of global sales data to find seasonal trends. That's analytical work, not infrastructure maintenance.
Makes sense. And the deck makes it very clear that you cannot just memorize your way through this stuff. They heavily advocate for utilizing the 90-day, $300 free trial, the free tier, and a gamified learning platform called the Arcade.
Because curiosity is a required skill here. Theoretical architecture is totally useless when a system is cascading into failure.
You have to physically provision these databases, break them, misconfigure the network routing, and then panic troubleshoot your way out of the mess to actually understand the failure modes. Right?
You really do. You have to experience the friction of setting up a cross-region read replica and watching the replication lag spike because you misconfigured the network bandwidth.
So, assuming our engineer has built a rock-solid understanding of these individual database components, they are immediately confronted with the massive architectural shift that dictates how all of these components actually wire together.
The shift to microservices.
Yes. The blueprint states unequivocally that Google Cloud favors microservices over monolithic applications. So we need to dissect why an industry would willingly abandon the simplicity of a monolith.
Well, the legacy monolith was a necessary evil of a time when computing resources were incredibly scarce. In a monolith, you compile your user authentication logic, your inventory management, your payment processing, and your recommendation engine into a single massive binary file.
And you deploy that single file onto an application server, and all of that code talks to one giant, centralized relational database.
Right, and the appeal is obvious. End-to-end testing is trivial because everything runs in the same memory space.
Huh.
If the payment code needs to check if a user is authenticated, it just calls a function.
It's a closed, predictable ecosystem.
Exactly. But the predictability vanishes the moment you try to scale. The primary failure mode of a monolith is the blast radius.
The blast radius.
Yeah, so if a junior developer pushes a memory leak in the recommendation engine, that memory leak consumes all the RAM on the server. Suddenly, the payment processor crashes because it can't allocate memory.
Oh, wow. So a bug in a non-critical feature takes down the entire revenue-generating pipeline.
Exactly, not to mention the human bottleneck. If you have 1,000 engineers all trying to merge code into one monolithic repository, the deployment pipeline becomes a traffic jam.
The code base becomes a bowl of spaghetti where, changing a database column for the inventory team silently breaks a SQL query written by the analytics team 3 years ago.
Right. So to escape that blast radius and the deployment friction, the industry moved to microservices. You take the monolith and shatter it. The payment processor becomes its own independent application managed by a dedicated team.
But the golden rule of microservices The architectural law that completely redefines the database engineer's job is that storage must be completely isolated.
Yes. You cannot shatter the application tier into 100 microservices, but keep them all tethered to the same legacy monolithic database.
Why not?
Because if you share the database, you've achieved nothing but adding network latency to a monolith. If the pricing microservice and the catalog microservice read and write to the same relational tables, they are tightly coupled.
So the pricing team couldn't alter a table schema without organizing a multi-department meeting.
Right. The agility of microservices is predicated on complete autonomy. Therefore, every microservice gets its own dedicated database, customized entirely for its specific workload.
Okay, here's where it gets really interesting. Moving from a monolith to microservices sounds like moving out of a massive shared house into an apartment building.
Okay, I like where this is going.
So in the legacy monolith, you and 10 roommates share one giant industrial refrigerator. Making a complex meal is easy because every ingredient you could possibly need is on one of the shelves. You just open the door and grab what you want.
Right, and the apartment building represents the microservices architecture. Everyone has their own isolated apartment with their own specialized mini-fridge. The vegan roommate has a fridge optimized for produce. The roommate who only drinks energy drinks has a fridge that is just a cooling rack.
Exactly. But the logistical nightmare begins when you try to cook a recipe that requires ingredients from 3 different apartments. You have to walk down the hall, knock on the door, ask for the eggs, hope they're home, wait for them to hand it to you, and then go to the next apartment for the milk.
That is a perfect analogy. And in cloud architecture, that logistical nightmare is called distributed transactions. And it is arguably the most painful problem a database engineer has to solve.
So how do you solve it? Because it sounds like a mess. Let's look at the mechanics of a transaction in the old monolith first. A user clicks buy.
Okay, so the application tells the single database to deduct the item from inventory and then add the charge to the user's billing table. The database locks both of those tables simultaneously. It makes the changes. If the billing step fails for some reason, the database automatically rolls back the inventory deduction.
It's an atomic transaction. The system is perfectly safe.
But in the microservices apartment building, the inventory data is locked inside the inventory services Postgres database, and the billing data is locked inside the billing services NoSQL database. They cannot talk directly to each other.
And if they can't talk directly, you have to orchestrate a transaction across a network. So what happens if the inventory service successfully deducts the item, sends a network request to the billing service to charge the card, and like a router between them fails?
The network connection drops. The inventory service thinks the transaction is moving forward, but the billing service never received the instruction. You now have an inconsistent state. Money wasn't collected, but the inventory is gone.
The naive approach would be to try and lock both databases over the network at the exact same time, right? Like a two-phase commit. You send a message to both saying, prepare to lock, wait for them both to acknowledge, and then say commit.
You could, but two-phase commits are absolutely toxic for performance at scale. If the billing database is running slightly slow, the inventory database has to sit there completely locked, waiting for the network to resolve. In a high-throughput system, locking databases over a network will grind your entire application to a halt within seconds.
So the blueprint solution to this is what they call loose coupling and asynchronous communication. Instead of demanding immediate synchronized confirmation, you rely on eventual consistency and event-driven patterns, like the saga pattern.
Yes, the saga pattern. It replaces the network lock with a sequence of local transactions. So the inventory service deducts the item in its own database. It then publishes an event to a message broker, like Google Cloud PubSub. The message just says, item 123 reserved for user 456.
And then the inventory service is done, it releases its locks, and moves on to the next customer.
Exactly. Meanwhile, the billing service is subscribed to that message broker. It sees the message, picks it up, and attempts to charge the card in its own separate database.
Hey, what if the billing service goes offline for 10 minutes?
It doesn't matter. The message waits patiently in the queue. The inventory database isn't locked. When the billing service reboots, it processes the queue.
Oh, wow. But what if the credit card is declined?
Then the billing service publishes a new message to the broker. Payment failed for user 456. The inventory service reads that failure message and runs a compensating transaction to add the item back to its database.
It requires significantly more code, but it totally eliminates network locks and allows the system to scale infinitely.
Yes, it's brilliant.
So if every single microservice is locked in its own isolated apartment with its own customized mini fridge, the obvious question becomes, how do you choose the right fridge? Because buying a massive, expensive relational freezer for a service that just needs to store a few unstructured JSON documents is a fast way to bankrupt your cloud architecture.
It really is. And that dilemma forces us to confront the biggest religious war in database history, SQL versus NoSQL.
The Great Divide.
The Great Divide. And the division between SQL and NoSQL is fundamentally a debate about the physical limitations of hardware versus the logical limitations of data structures. Let's examine standard SQL or relational databases first. The architecture is built entirely around strict normalized tables.
You define schemas with rigid columns and data types, and you establish foreign keys to relate a row in the customer table to a row in the orders table.
And the rigidity is the point. Relational databases enforce ACD compliance. Atomicity, consistency, isolation, durability. It is the ultimate guarantee of data integrity.
So if I write a complex query that updates a user's balance and transfers money to another account, the database ensures that either every single step succeeds or the entire operation is rolled back as if it never happened.
Now, it will never allow a partial success where money just disappears into the ether. But enforcing that AC guarantee requires immense coordination. When you update a row in a relational database, the engine has to navigate a B-tree index, locate the physical block on the storage disk, apply a write lock so no other process can touch it, write the data to a transaction log, update the data pages in memory, and then guarantee that it is written to permanent storage.
That's a lot of steps. And because of that intense need for centralized coordination and memory management, relational databases traditionally hit a physical ceiling, right? They scale vertically.
Vertically, yes. If your Postgres database is maxing out its CPU, your only option is to shut it down, migrate the data to a more expensive server with a faster processor and more RAM, and turn it back on. You are fundamentally limited by the size of the biggest motherboard you can buy.
You cannot easily take a traditional relational database and spread it across 50 cheap computers because executing a complex SQL join across 50 different network boundaries while maintaining strict write locks would just introduce unbearable latency.
Exactly. So as the internet exploded and applications started demanding millions of read and write operations per second, engineers realized they had to sacrifice the strict coordination of ACID to break the physical limits of a single machine.
Which birthed NoSQL, the non-relational database.
Right. The fundamental premise of NoSQL is horizontal scaling. Instead of buying $1 million supercomputer, you buy 1,000 cheap commodity servers. But to make that work, you have to abandon the complex relational tables and foreign keys.
You abandon them because you can't guarantee that the customer record and the order record will live on the same physical machine.
Exactly. In NoSQL, data is usually sharded based on a hashing algorithm. When you save a user profile, the database hashes the user ID, and that hash determines which of the 1,000 servers will hold that specific piece of data.
And because the data is scattered, maintaining strict, instantaneous ACID consistency across the entire cluster is practically impossible without freezing the whole system. So NoSQL databases trade ACID for base.
Basically, available, soft state, eventual consistency. Base is an engineering compromise that prioritizes uptime and partition tolerance over absolute accuracy.
So basically, available means the system guarantees a response to any request, even if a significant portion of the servers in the cluster have crashed. It will find a replica somewhere and serve the data.
Right. Soft state acknowledges that the system is constantly replicating data in the background, so the state is fluid. And eventual consistency is the crucial trade-off here.
We touched on eventual consistency earlier with the batch job scenario, but in a live application, it means that if I update my profile picture, the server in New York gets the update instantly, but it might take 2 seconds for that update to replicate to the server in Tokyo.
Yes. And if a user in Tokyo requests my profile during those 2 seconds, they get the old picture. But for 99% of web applications, that just doesn't matter. A 3-second delay on a profile picture update is a perfectly acceptable trade-off for a database that can handle 100,000 writes per second and survive a data center fire.
You mash the data model to the use case, and the blueprint breaks the NoSQL landscape into specific tools for specific jobs, like document databases, like Google Cloud Firestore, stored data as free-form JSON objects. They are incredibly developer-friendly because you don't have to break an object into a dozen relational tables.
You just serialize the whole user object and save it as one document.
Then you have key value stores, like Memory Store or Redis, which strip the database down to its barest essentials. You have a unique key and a block of data associated with it. There's no query language to search inside the value. You either know the key or you don't.
And because of this simplicity, they operate entirely in RAM and can serve reads in microseconds, making them the ultimate caching layer.
Right. Then you have wide column stores like Bigtable, which are designed for monstrous data ingestion like time series metrics, and graph databases, which optimize for navigating the relationships between data points rather than the data itself.
Perfect for a social network trying to calculate the shortest path of connections between two users. But choosing between these options isn't just about the data shape. It comes down to a harsh mathematical reality known as the CAP theorem.
The CAP theorem. I've heard this explained with the old contractor joke. Fast, cheap, or good pick too.
Right, but in a cloud environment, that analogy kind of falls apart because you don't actually get to pick any two. You are operating over physical networks, routers, and undersea cables that you do not control.
Oh, because network partitions, the P in CAP are inevitable.
Yes, a backhoe will accidentally sever a fiber optic line. A router will crash. An entire availability zone will lose connectivity. So partition tolerance is not a choice. It is a mandatory requirement for survival. Your database nodes will get cut off from each other.
So you're really just choosing between C consistency and A availability. Let's visualize this. Imagine a bank with two branches, branch A and branch B, sitting on opposite sides of a river.
Okay, I'm picturing it.
The branches keep their ledgers perfectly synchronized by calling each other over a telephone line running across a bridge. That telephone line is the network. One day, a storm washes out the bridge and destroys the telephone line. The network partition has occurred. Branch A can no longer talk to Branch B.
Now the system is forced into the CAP theorem dilemma. A customer walks into Branch A and asks to withdraw $50. The teller at Branch A knows the customer has $100 in the local ledger, but because the phone line is dead, the teller cannot verify if the customer just withdrew $90 from Branch B 5 minutes ago.
So the teller has to make a choice. Option 1. The teller refuses the transaction. They say, I'm sorry, I cannot communicate with the other branch, so to guarantee absolute accuracy and prevent an overdraft, I am closing the bank until the bridge is repaired.
That is choosing consistency over availability. It is an ACID relational database. It guarantees the data is perfectly accurate, but it achieves that by refusing to operate during a partition. The system goes down.
Option 2. The teller gives the customer the $50 based on the local ledger, knowing there is a risk they might be overdrawing the account if they already visited Branch B, but prioritizing customer service and keeping the bank open.
And that is choosing availability over consistency. It is a base NoSQL database. It accepts the risk of a temporary data conflict to ensure the system never stops responding. When the bridge is rebuilt and the phone line is restored, the branches will sync their ledgers, realize the account was overdrawn, and resolve the conflict perhaps by issuing an overdraft fee.
That resolution is eventual consistency in action.
Exactly. And the database engineer's job is determining whether the business can tolerate the overdraft fee or if the system must halt entirely.
Grasping whether data needs to be locked down for consistency or set free for availability leads directly into the next massive divide in the blueprint. It's not just about how data is stored, but how the application attempts to process it. We have to dissect the dynamics of OLTP versus OLAP.
These two acronyms describe entirely antithetical workloads. OLTP stands for Online Transaction Processing. OLAP stands for Online Analytical Processing. They require completely different physical structures on the storage disk.
The blueprint characterizes OLTP as transaction-oriented applications dealing with a large volume of fast individual operations, like a user changing their password, a customer adding a single item to a shopping cart, an Uber driver updating their GPS coordinates.
These are highly targeted surgical operations. You're asking the database to search through a billion rows, locate one specific primary key, modify 3 columns of data on that row, and commit the change to disk instantly. To make that surgical strike efficient, OLTP databases use row-oriented storage. All the data for a single user is physically stored sequentially on the hard drive.
And to protect the integrity of those fast updates, OLTP relies heavily on data normalization. You break the data into dozens of interconnected tables to ensure that every distinct piece of information exists in one and only one place.
The physical benefit of normalization is update speed and consistency. If a customer changes their billing address, you update one single row in the addresses table. Because the orders table only contains a foreign key pointing to the addresses table, you don't have to touch the orders.
Because if you had duplicated the address onto every single order record, changing an address would require the database engine to scan the entire disk, find thousands of historical orders, and lock them all to update the text.
Right. Normalization keeps writes lightning fast.
But the exact architecture that makes writing data incredibly fast makes reading massive amounts of data incredibly slow. Which brings us to OLAP, Online Analytical Processing.
OLAP workloads are the domain of data scientists and business intelligence dashboards. The queries are not surgical strikes, they are carpet bombing. An OLAP query doesn't care about a single user's password. It asks questions like, calculate the average lifetime value of every customer acquired in Europe between 2018 and 2023, cross-referenced against the specific marketing campaigns they interacted with, grouped by the device operating system they used.
Wow. And if you attempt to run that query against a normalized OLTP database,
It will collapse. The database engine has to take the customers table, cross-reference it with the regions table, match that to the orders table, link it to the marketing table, and join it with the devices table. Executing multi-table joins across a billion rows requires an astronomical amount of CPU and RAM to hold the intermediate data structures in memory.
so to solve this, OLG databases like BigQuery abandon normalization entirely. They rely on massive denormalization. You intentionally duplicate data to avoid joins. You run a pipeline that takes the normalized data, flattens it out, and writes the user's region, device, and marketing campaign directly onto every single order record they ever placed.
Exactly. You are intentionally bloating the storage size by repeating the same text over and over again.
Which feels so wrong.
It does, but in cloud economics, storage space is incredibly cheap. But CPU compute time is incredibly expensive. Denormalization trades cheap disk space for expensive processing speed. Furthermore, OLAP databases often use columnar storage instead of row-oriented storage.
Why does columnar storage matter for analytics?
Because instead of storing all of user A's data together, it stores all the values for the device type columns sequentially on the disk. So if your analytical query only wants to know the average order value by device type, the database engine only has to read the physical blocks on the disk containing the order value column and the device type column. It completely ignores the terabytes of data containing usernames, addresses, and passwords.
It reduces the disk I/O by orders of magnitude, allowing BigQuery to scan petabytes of data in seconds.
Precisely.
So what does this all mean for the user? Is OLTP the cash register ringing up my coffee? And OLAP is the corporate headquarters analyzing coffee sales across 1,000 stores at the end of the year.
That is exactly right. The database engineer builds the cash register, Cloud SQL, or Spanner, while the data engineer builds the system that ships that data to corporate, which is BigQuery.
Okay, so now that we have all these options, NoSQL, OLTP, OLAP, how does an engineer actually make a decision in the real world or on the exam?
That requires a systematic framework, which the blueprint outlines as the It Depends matrix. It forces you to evaluate availability, consistency, performance, scalability, and cost.
What I find most fascinating is how this matrix highlights the evolution of how we actually procure computing power. The blueprint breaks sizing and growth models into 3 distinct eras of cloud abstraction.
Right. The lowest level of abstraction is the pre-allocated model. This is infrastructure as a service. You're renting virtual machines using Google Compute Engine, or you're provisioning a Cloud SQL instance. You have to act like a traditional hardware planner. You specify the exact number of CPU cores, the gigabytes of RAM, and most importantly, you provision a specific volume of persistent disk storage.
The danger here is capacity planning, right? If you provision a 2 terabyte disk and your app only uses 50 gigs, you're still paying for the entire 2 terabytes every month. The capacity is pre-allocated and trapped.
Conversely, if your viral app suddenly ingests 3 terabytes of data, your disk fills up, the database halts, and your application crashes. You are responsible for monitoring the disk space and manually resizing it.
Though managed services like Cloud SQL do offer automated storage increase features to mitigate this, you're fundamentally still managing virtual hardware.
Yes. The next era of abstraction is managed services, specifically referencing massive systems like Cloud Spanner and Cloud Bigtable. Here, you're no longer provisioning hard drives. You provision compute capacity in the form of nodes.
So you tell Google how much processing horsepower you need to handle the traffic.
Right. A Spanner node provides a certain amount of read and write throughput. The storage itself decouples from the compute. You pay for exactly the gigabytes of storage you consume without pre-allocating a drive.
However, there are physical constraints tied to the compute nodes. The blueprint notes that to maintain Spanner's incredible performance, it's recommended to keep the storage ratio to around 4 terabytes per node. If your data grows beyond that, you must provision another expensive compute node just to rebalance the storage load.
Which leads to the final era, the absolute apex of cloud engineering, serverless databases. The blueprint lists Google Cloud Storage, BigQuery, and Firestore. In a true serverless model, you do not provision CPUs, you do not configure RAM, and you do not allocate storage. You just throw data at the API and it handles it.
But wait, if I don't allocate storage, where does it go? Is the cloud just like an infinitely expanding balloon?
It feels like it, but under the hood, Google completely separates the storage architecture from the compute architecture. When you load data into BigQuery, it's stored in Colossus, Google's distributed file system, sliced into tiny encrypted blocks and scattered across tens of thousands of physical disks.
And when you run a query,
BigQuery uses its Dremel execution engine. It analyzes your SQL statement, and in a fraction of a second, it reaches into a massive multi-tenant pool of dormant CPUs, grabs thousands of virtual workers, assigns each worker a tiny slice of your data in Colossus, executes the query in parallel, aggregates the results, returns them to you, and immediately releases the workers back to the pool.
that is mind-blowing.
You utilize 10,000 servers for 2 seconds, and you only pay for the exact amount of data those servers scanned.
That paper query model is a double-edged sword. With a provisioned Cloud SQL instance, your monthly bill is perfectly predictable. It might be $500 a month, whether you run 10 queries or a million queries. The hardware is capped.
Right.
But with serverless BigQuery, if an inexperienced engineer writes a highly inefficient SQL join without partition filters and accidentally commands the Dremel engine to scan 3 petabytes of historical data for a simple dashboard.
Oh, the serverless engine will happily execute the command. It will spin up the resources, scan the 3 petabytes in 20 seconds, and immediately charge your billing account thousands of dollars for a single query.
Ouch.
Yeah, the operational ease of serverless transfers the risk from infrastructure maintenance directly to financial management. The database engineer has to implement strict quota controls and billing alerts to prevent catastrophic runaway costs.
Okay, so choosing the right database is great for a new app, but what happens when an enterprise already has decades of data sitting in an old data center? Getting that data into the cloud is a massive focus of the exam.
Right, the migrations. The blueprint categorizes migrations into homogeneous and heterogeneous strategies. Homogeneous migrations are the path of least resistance. You're moving from an on-premise database to the exact same engine in the cloud, like local Postgres to Cloud SQL Postgres. The schema remains identical. The application code remains identical.
The challenge is purely logistical. How do you move the data without incurring unacceptable downtime? The blueprint lists export, import, and backup restore. You dump the database to a file, upload it to cloud storage, and restore it. But that requires taking the application offline for hours while the massive file transfers.
Which is why enterprise migrations rely on replication.
Yeah.
You set up a secure VPN tunnel, configure the Cloud SQL instance as a read replica of your on-premise database, and let them synchronize over the network.
Once the cloud database catches up and the replication lag hits 0, you take a brief 5-minute downtime window, sever the connection, promote the cloud database to the primary role, update your application's DNS records, and you are running in the cloud.
But the real trial by fire is the heterogeneous migration. This is moving from a legacy Oracle relational database to a NoSQL document store like Firestore, or moving from an on-premise SQL server to Google Cloud Spanner.
Because it's not just moving data, it's a deep architectural transformation. You're changing the fundamental data model. You have to analyze hundreds of normalized relational tables and figure out how to collapse them into denormalized JSON documents.
Every single SQL query embedded in your application source code must be rewritten to use a NoSQL API. It is an incredibly high-risk endeavor that requires months of planning, dual writing data to both systems simultaneously, and extensive validation.
The blueprint also contrasts 2 methods of moving data continuously: standard replication versus CDC, or change data capture. We just talked about replication for migrations where it mirrors the entire database, but CDC, handled in GCP by a service like DataStream, is completely different.
Right. Replication is blunt force. It synchronizes the entire disk state. CDC is a surgical extraction of business events. Most relational databases maintain a write-ahead log, or WAL. Before the database writes a change to the physical table, it appends a record of the change to this sequential log. It's a safety mechanism for crash recovery.
So CDC tools tap directly into that log.
Exactly. Data stream reads the write-ahead log in real time. It doesn't query the tables and slow down the production database. It just reads the exhaust pipe. It captures every single insert, update, and delete event, formats them into a standardized stream, and pipes them into a completely different system.
You use CDC when you want to take every single transaction happening in your Cloud SQL operational database and stream it in near real time into BigQuery for analytics without putting any read pressure on the operational database.
Right. But when we talk about these data streams and replications moving across the globe, we run into the physical limits of the universe again. The blueprint emphasizes the difference between synchronous and asynchronous replication, and this entirely comes down to the speed of light through a fiber optic cable.
So in a synchronous replication setup, when a user attempts to write a record to the primary database, the primary immediately sends the payload over the network to the replica. The primary database will not acknowledge the commit to the user until it receives a confirmation receipt back from the replica.
It guarantees absolute zero data loss. If the primary server instantly bursts into flames, the replica is guaranteed to have the exact same data, but the cost is latency. The user's application is hanging, waiting for that round trip.
Right. Light travels through fiber optic glass at roughly 200,000 kilometers per second. If your primary database is in Iowa and your replica is in a different data center in the same zone in Iowa, the distance is short enough that the round-trip network latency is under a millisecond.
The user never notices the delay. Therefore, you use synchronous replication for high availability within the same geographic region.
But if you want disaster recovery, if you are terrified that a hurricane will wipe out the entire East Coast, you need a replica in London or Tokyo.
And the physical distance between Iowa and Tokyo introduces a baseline physics latency of over 100 milliseconds, not counting the time required by network switches and routers. If you require synchronous replication to Tokyo, every single write operation in your application will take a quarter of a second just waiting for the network. In modern web standards, a quarter-second database lock is an eternity. It will destroy your throughput.
So for cross-region disaster recovery, you're forced to use asynchronous replication. The primary database commits the write locally, instantly tells the user, "Success, your data is saved," and then in the background, it begins transmitting the data to Tokyo.
Tokyo might be a few milliseconds or even a few seconds behind the primary. It is eventually consistent. The risk is that if a meteor hits Iowa in the 2 seconds before the data replicates, that data is permanently lost, even though the user was told it was saved. The database engineer has to quantify that risk, known as the recovery point objective, and design the architecture accordingly.
Okay, let's unpack one more massive architectural concept before we get into the economics. Dealing with massive data sets on a single system, the blueprint draws a very sharp distinction between partitioning and sharding.
Yeah, they're both techniques for breaking massive tables into manageable chunks, but they operate at entirely different levels of the hardware stack. Partitioning happens on a single physical machine within a single database instance. You configure the database engine to logically divide a massive table into smaller physical files on the disk, usually based on a time boundary.
So is partitioning like organizing my filing cabinet into folders by year? Like all the logs for January are stored in one block on the disk and February in another?
That's a great way to think about it. And the immediate benefit is query performance. If a developer runs a query looking for an error that happened in March, the database engine ignores the January-February partitions entirely. It reduces the disk I/O. Furthermore, it simplifies data lifecycle management. You can configure the database to simply drop the partition containing data older than 7 years, which instantly deletes millions of rows without having to run a massive CPU-intensive delete query.
So partitioning is organizing the data within the single machine you have, while sharding is like buying 3 extra filing cabinets and putting them in different rooms.
Exactly. Sharding is horizontal scaling for relational databases, and as the blueprint warns, it is notoriously difficult to implement and maintain. In a sharded architecture, you break the database across multiple independent physical servers. Customers A through M are stored on server 1. Customers N through Z are stored on server 2.
And the nightmare begins when you try to run a query across the shards, because it breaks the fundamental promise of SQL. If you want to join a table on server 1 with a table on server 2, a traditional relational engine cannot do it.
Right. You have to write complex logic directly into your application code to query server 1, query server 2, bring all the data into the application's memory, and manually merge the results. Managing schema changes, backing up the cluster, and ensuring data consistency across the shards becomes an operational nightmare.
Which is exactly why Google built Cloud Spanner to solve this exact problem invisibly. It's a relational database with strict SQL semantics that scales horizontally across thousands of machines globally, but it handles the sharding, the replication, and the distributed transactions completely invisibly to the user.
But to achieve that, Spanner had to solve the distributed time problem. In a normal distributed database, you cannot trust the timestamps on different servers because the internal quartz clocks drift. If server A says a transaction happened at 12.000.01 and server B says a conflicting transaction happened at 12.00.02, you can't be absolutely sure server A actually happened first. The clock on server A might just be 2 seconds slow.
And if you can't guarantee the exact order of events across a global network, you cannot provide AC consistency.
Exactly. So Google created the TrueTime API. They installed highly precise atomic clocks and GPS receivers into every single one of their data centers. TrueTime provides a highly accurate synchronized time signal with a known margin of error, usually just a few milliseconds.
Wow.
When Spanner commits a distributed transaction, it intentionally waits out that tiny margin of error before confirming the commit. That infinitesimal pause guarantees that no other transaction in the world could have been assigned an overlapping timestamp. It's hardware engineering solving a software limitation.
It's absolute science fiction, but that level of engineering brings us crashing into the reality of Section 7, security, economics, and vendor lock-in. With data moving across regions, syncing globally, and sitting on serverless platforms, how do we keep it safe and avoid going bankrupt?
Let's look at the encryption options, because there is a brutal paradox buried in this blueprint. By default, Google Cloud encrypts all data at rest, they manage the keys, they rotate the keys, and the effort for the customer is zero. For the vast majority of compliance frameworks, this is entirely sufficient.
But some highly regulated industries, defense contractors, specialized healthcare, demand granular control over the cryptographic keys. That introduces the middle tier, CMEK, Customer Managed Encryption Keys via Cloud Key Management Service.
With CMEK, the cryptographic keys still physically reside in Google's cloud infrastructure, but the customer controls the lifecycle. You define the rotation schedule. Crucially, if you detect a breach, you can instantly disable or destroy the key via an API call.
Even if the data is sitting on Google's hard drives, the moment that key is destroyed, the data becomes mathematically unreadable permanent ciphertext. It gives you a cryptographic kill switch.
But the blueprint outlines an even more extreme option. CFKey, customer-supplied encryption keys. In this model, you do not let Google store the key at all. You generate the key in your own on-premise hardware security module. When you want to read or write data to the cloud, you transmit the key alongside the API request.
So Google uses the key entirely in volatile memory to perform the encryption or decryption, and then drops the key. It is never written to a disk. It is the ultimate zero-trust security posture. You are proving that Google cannot access your data even if served with a subpoena because they literally do not possess the key to decrypt it.
But here's the paradox. If I'm paranoid about Google seeing my data, I should use CSE, right?
Right.
But if you demand CSE, you cannot use Cloud SQL, you cannot use Spanner, you cannot use BigQuery or Firestore.
Wait, really? Why not?
Because managed services rely on background automation. BigQuery needs to be able to autonomously read your data at 3 a.m. to run an optimization routine. Spanner needs to read your data to rebalance shards across servers. If you withhold the encryption key, those automated systems are locked out.
So I'm basically just renting a dumb hard drive from Google at that point.
Yes. CSEK is only supported on raw compute engine virtual machines and raw persistent disks. The paradox of ultimate security is that you sever yourself from all the advanced managed services of the cloud. You have to build the entire database stack yourself.
That is a staggering trade-off, and there's a similar paradox when we look at cloud economics, specifically the battle between CapEx and OpEx.
In the traditional data center world, IT was a capital expenditure, or CapEx.
Yeah.
You spent 6 months projecting your capacity needs for the next 5 years. You wrote a multi-million-dollar check to buy physical servers, install them in racks, and depreciated the asset over time. It was a rigid, upfront financial planning.
The primary marketing pitch of the cloud was the shift to operational expenditure, or OpEx, the utility model. You spin up a server, you pay per second of usage, and you shut it down when you're done. The blueprint highlights that per-second pricing gives you infinite elasticity.
But the reality of enterprise finance departments is that they despise unpredictable OpEx bills. They cannot budget for a cloud bill that fluctuates by hundreds of thousands of dollars a month based on developer usage or traffic spikes. They demand predictability.
So the cloud providers created committed use discounts, or CUDs. The exam blueprint explicitly advises using CUDs to cost-optimize workloads.
Right, a committed use discount is an agreement where you promise to pay for a baseline level of compute resources for 1 or 3 years, regardless of whether you actually use them. In exchange, Google gives you a massive discount, sometimes up to 70% off the on-demand price.
The paradox is that to achieve the best possible cloud economics, enterprises are forced to abandon the flexible pay-as-you-go OpEx model and commit to multi-year contracts, effectively recreating the rigid financial planning of the on-premise CapEx era.
It all comes full circle.
It really does. The final concept we need to unpack is the constant shadow hanging over all these decisions: vendor lock-in. The blueprint defines it simply as a state where a customer cannot easily transition away from a competitor's product.
The standard industry advice is to avoid it at all costs, usually by leaning entirely on open source software. If you build your application purely around open source Postgres
Right.
and you deploy it on Cloud SQL, your lock-in is minimal. If Google raises their prices astronomically, you can take your standard SQL schema, export your data, and spin up an Amazon RDS Postgres instance in a weekend.
But the blueprint explicitly warns that utilizing almost any managed NoSQL engine will result in vendor lock-in. If I architect my microservices to use Google Firestore, I am writing application code that uses proprietary Google libraries to interact with a proprietary Google document structure.
You cannot easily migrate a Firestore application to AWS DynamoDB. The data models are different, the consistency guarantees are different, and the APIs are fundamentally incompatible. Migrating away would require rewriting the data access layer of your application entirely.
So should an architect avoid Spanner, BigQuery, and Firestore just to keep an exit strategy open?
That is the ultimate strategic question. The blueprint suggests that you should accept vendor lock-in when it makes clear business sense. Building a perfectly cloud-agnostic architecture where you abstract everything behind your own custom interfaces, just in case you want to switch providers in 5 years, carried an immense engineering cost.
You end up building for the lowest common denominator.
Exactly. You deny your developers the speed of Firestore, the global consistency of Spanner, or the analytical power of BigQuery out of fear of a migration that might never happen. Often, the operational agility and time-to-market advantages of fully embracing proprietary managed services far outweigh the theoretical risk of being trapped.
We have dissected an unbelievable amount of architecture today. I mean, we started by drawing a hard line around the database engineer, identifying them as the trauma surgeons managing the physical limits of the transactional vault, completely distinct from the data pipelines of the data engineer.
We trace the chaotic evolution from brittle monolithic applications to the isolated mini-fridge architecture of microservices. We explored how the saga pattern prevents distributed transactions from locking up the network.
We examined the physical reasons why relational SQL databases scale vertically due to the demands of strict ASIC consistency, while NoSQL databases scale horizontally by embracing the eventual consistency of base. And we saw how the CAPT theorem mathematically forces us to choose between availability and consistency the moment a network partition severs our servers.
We look at the disk-level differences between the fast, row-based normalization of OLTP systems and the massive columnar denormalization required by OLAP engines like BigQuery.
We navigated the sizing models from pre-allocated virtual machines to the operational magic and financial danger of serverless architecture. We covered the latency physics dictating asynchronous replication, the atomic clock engineering behind Cloud Spanner sharding capabilities, and finally, the paradoxes of ultimate encryption, committed use discounts, and the strategic embrace of vendor lock-in.
It is a breathtaking ecosystem of engineering trade-offs. And as a final thought to leave you with, consider the trajectory we've mapped out today. We started with engineers managing physical hard drives, moved to provisioning virtual machines, then to allocating compute nodes, and finally to serverless platforms like BigQuery and Firestore, where the infrastructure is entirely abstracted away.
Right.
As serverless databases abstract away more and more of the underlying hardware nodes and storage allocations, will the database engineer role eventually disappear entirely, leaving only data modelers who never once have to think about a server? Are we looking at a future where we only need people who define the logical shape of the data while the AI-driven control plane handles every physical reality beneath?
It is wild to think we might be dissecting a certification for a role that is actively automating itself into obsolescence. But until the machines completely take over the infrastructure, somebody has to understand how the vault actually works. I challenge you to actively apply this mental model today. The next time you open a massive global application, your banking app, or a ride-sharing service, mentally map the architecture.
Ask yourself if the transaction you just executed required the strict ACD lock of a relational database or the horizontal scale of a NoSQL document store.
Try to visualize the microservices communicating asynchronously behind the scenes. Because once you understand the physical and logical laws governing these systems, you stop being overwhelmed by the fire hose of cloud terminology, and you start seeing the matrix of engineering decisions that hold up the modern world.